737 very high. ये कोई कंडक्टर है मुझका करूंगा ठीक है सामने बता रहा हूं
बोलो
सर म्यूट कॉल कर दीजिए सर
यस so during the characteristic of PN junction diode we have taken voltage current and this is a forward characteristic and this is your reverse characteristic. So this region from here to here we are called as breakdown region. Why? After this VBR or breakdown voltage, huge amount of current will flow and that cannot sustain in the diode will burn. So that's why this is called as breakdown region. But this is actually demerit of diode. But we can take this disadvantage as one of the advantage here. So breakdown diodes means the diodes which can operate in breakdown region. So the PN junction diode which are operated in breakdown region of reverse voltage is called or are called breakdown diodes. These diodes, if I take this type of diode, they will operate in reverse bias even in breakdown region. Even high amount of current will flow through them, they will not burn or they will not break. So those diodes are called as breakdown diodes. What is the use? We'll see. Now, why these are sustaining this voltage? Because they are designed with sufficient power dissipation capacity. More current will flow means what? It will generate more heat. So more heat means in that area or in that diode area, if huge amount of power will generate, then it will burn. So here the specially designed diodes which are sustaining this high power, so they are designed, some fabrication steps are different and some parameter we will consider during this fabrication of this breakdown special diodes. Okay, now here we will understand what is the application of these breakdown diodes and why this breakdown occurs. That means why after this VBR the current will increase suddenly. So what is the reason? We'll discuss here. Generally, two processes are there. One is avalanche breakdown, another one is Zener breakdown. So due to these two processes, the current will increase after breakdown voltage. So one by one we will discuss. So first we will discuss avalanche breakdown. Do you know what do you mean by avalanche? You have heard in Himalaya region avalanche occurs and our soldiers are martyred there. So what do you mean by avalanche? What is the general meaning?
Flood.
Huh?
स्नो स्लाइड कर जाती है.
Sudden change or sudden increase, right? Himalayan region में जो होता है sudden the ice cake which are boiling or movement happened. Due to that, this snows are moving one side to other side. Due to this accident happened. Here also, if we observe after VBR, sudden increase in current happens. Okay, so that's why that is called as avalanche breakdown. If you look at the actual region, let us see. If I'll take a PN junction diode here, and reverse bias it. Okay. Now, due to that, depletion region will increase. Will observe depletion region here. Now, when I increase this voltage, right? Initially, very small leakage current. If I draw the characteristic, it will be like this. So initially, leakage current is this much. So I'm increasing the voltage more and more. Then, After certain voltage, the current will increase from this point. So how we'll analyze why this behavior is current is increases here in reverse direction? We will try to understand here. During the PN junction operation, we have discussed in the forward bias what happens. The majority carrier is flowing from P side to N side after this depletion region omits or erase. But in reverse bias condition, majority current will not flow or majority carrier will not flow from one side to other side. That means holes cannot flow from P to N, electron cannot flow from N to P. But the generated electric field which are here, they can easily flow the electrons and holes which are present in the P and N side as minority carrier. So holes can easily flow this side, electrons are easily flow this side. So that's why we are getting current in the opposite direction. Okay, just a minute. Hello. Class chalta online. So this is your I minority. Yes or no? Do you remember this concept?
Sir, could you repeat the last statement once?
Last statement what I have given here, if you during the depletion region or during the reverse bias, the depletion region, minority carriers are present, electron in the P side and hole in the N side. So due to this development of depletion region on positive and negative ion, electric field generated, and due to this electric field, the minority carriers can flow from one side to other side. So electrons are moving from P to N and holes are moving from N to P easily.
Yes, sir.
So due to that, we are getting minority carrier whose direction is, what is the direction? Holes are moving from
Sir,
right
N to P.
N to P. So this is your minority current. Now, at the same time, we are increasing the reverse voltage. When I increase the reverse voltage, what happened? I am actually giving some type of energy here. Voltage is increases, means I am giving energy. So the electrons which are present here or the holes present here, let us assume these are the carriers, free carriers, which are moving with some velocity. And when I increase this voltage, they will gain more energy. When they are gaining more and more energy, they will move faster. So move faster means what? Suppose the electron is present here and let us take the electron is present at the edge here. While it is moving, it will collide with another atom. Let us take this is neutral atom. Or I'll take another, let's say electron is here, it is traveling. It will have high energy, so neutral atom is present here. When electron will collide with this neutral atom, what will happen? Transfer of energy will happen or not? क्या होगा? When electron is moving with very high speed with particular energy and it is colliding with a neutral atom means, let us say this is silicon atom which is present here, and in the valence shell 4 electrons are present. Okay, now this electron is colliding here, so that means it is transferring some energy to the system or to the atom. That means this energy is captured by this electron, and this electron will out of this atomic structure. So I'll get free electron as well as the vacancy which is created. I'll get one hole, or in terms, I can say one electron hole pair generated due to this collision. Yes or no?
Yes, sir.
So,
Now, if I see one electron is traveling during this collision, I am getting the original electron plus one extra generated electron, this one, and one hole. Now, this electron will generate another 4 electron with one hole. This electron will generate not 4, 2. Original electron, it will generate another electron. This electron will generate one electron with original electron with one hole. Like that it is moving. So from point 1 to point 2 to point 3, how many electrons are generated? I am sending one electron. During this travel, it has generated 1 to 2 to 4 electron. Yes or no?
yes, sir.
Now
Yes, sir.
electrons will move this direction and hole will move in opposite direction. This is the moment of electron, this is the moment of hole. Now come to the diagram what I have shown here. Electrons are moving in this direction. During this movement, it will generate more number of electrons. Whatever holes are generated, they will move this side. So this is the hole moment, this is the electron moment. And once these carriers are generated more and more, the concentration here as magnetic carrier will increase or decrease. During this repeated collision, one electron generating two electron will generate four electron generate 8 electron. Like that, the electron as well as number of holes in the depletion region will increase. Due to that, the magnetic current will also increase. Are you getting my point?
Yes, sir.
So this is actually happening due to the applied reverse voltage, but it is not of sudden. After certain point, means if you increase the voltage in reverse bias, then after certain point, the electrons or the magnetic carrier which are present in this depletion region will get enough energy and they will accelerate it with high speed, high velocity, and this collision will happen, and this will be repetitive collision or cumulative process. The process of generating the carriers are cumulative nature. That means one electron will generate 2, 2 will generate 4, 4 will generate 8, like that it will be continue. So during that process, the large number of carriers are generated and that will increase the leakage current. So that was written here. With increasing reverse bias voltage, electric field across junction increases. At certain reverse bias, electric field imparts sufficient high energy to thermally generated carriers crossing the junction. These carriers collide with another atom, break covalent bond, produce more free electrons. Newly generated carrier produce more free electrons, and this is cumulative process to generate high current. And this is called as impact ionization. Impact ionization means it is hitting with stationary electron. So this, due to this impact, the electron and hole are generated. That's why it is called as impact ionization. The process is called as impact ionization, and it will generate or it will cause this avalanche breakdown. Okay, so avalanche means due to this cumulative increase in magnetic carriers, current will increase and it will break down. So avalanche breakdown generally occurs in lightly doped diodes where depletion region is wider. Okay, that means if the depletion region is wider, it will have more area to cover. The electron is traveling this much of distance. So during that process, it will have many number of collision. So as many number of collision will there, that many number of carrier will multiply. So that is the origin of this avalanche breakdown. So we can say generally where we see like PN junction, normal PN junction diode, generally the P and N type are lightly doped. Due to lightly doped region, the depletion region is wider. Again, that is from charge neutrality principle. We have one concept where you can assume, you just remember this point, that lighter dope means wider depletion region, heavy dope means narrow, or the depletion region will be narrower compared to earlier case. Okay, so doping plays very important role. So doping increase means depletion region decrease. Okay, this concept is used very much here. So the diodes where Zener diode, or the diodes where we observe other type of breakdown like Zener breakdown, that are generally heavily doped diodes. But in normal diode, we observe this avalanche breakdown, and generally it occurs greater than 6 volt, means it is reverse voltage minus 6 volt will be there. If I plot, then this will be around minus 6 volt, more than minus 6 or around minus 6 volt. Okay, but in case of Zener diode, we'll see that will be less than 6 volt. So what are the point you have to note it here? First thing is, here collisions are happening, or cumulative process, repeated collision are happening. Due to that, the magnetic areas are generated, and this process is called as impact ionization, and it is occurring in lighter dope region or lighter dope diodes, where the depletion region is wider, or we can say the P side and N side depletion region penetrate more compared to heavy dope side. Okay, and it occurs greater than 6 volt. So these 4-5 points you can remember to describe this thing.
Sir,
Yes.
sir, and generally it occurs at greater than 6 volt, but you told something about minus 6 volt.
Reverse na.
Okay, okay, sir.
We are discussing about the breakdown. Breakdown is occurring only at reverse condition. So reverse means that is ultimately this minus sign will be added. So here only magnitude is written, right? Because whenever we draw any characteristic, how we'll draw? Like this, right? So this will be 6 volt means what? This is negative voltage, so minus 6 volt. Magnitude, if you take, it is 6 volt, so it is written as magnitude 6 volt. But actually reverse 6 volt if you say, then that will be minus 6 volt. Understood?
Yes, sir. Yes, sir.
Now let us see this Zener breakdown. Okay, this is a little bit similar to this one. If you observe here, let me draw another diagram. Here, this will be heavily doped. P plus, N plus I am writing to show the depletion region is narrow. So previously a little bit wider, now it is narrow. Okay. Now when I increase this voltage, that means in reverse voltage, what will happen? The volt per width, or electric field strength, that means E per unit area, how much, whenever I am increasing this voltage, how much electric field will generate divided by this area, because the depletion region is narrow, so area is less, so this strength, electric field strength, will increase very high compared to this one. You see the previous case, it is wider depletion region, so how much generated electric field, that will be distributed by larger area, so it will be decreased. Okay, but in this case, here area is small, or the depletion region is narrow, so this field strength is very high. Same thing is happening here. We are increasing means we are giving energy, and the electric field strength is increasing, but here the difference is that the strength is increasing due to lesser depletion region. Then what will happen? Due to that, the extra, or the atoms which are present in this depletion region, let me take here without, okay, whatever atoms are present here, because this is bonded with solid structure, so whatever electrons are present here, holes are present here as a magnetic area, they will move, and whatever neutral atoms are present, or ions are present, they will gain extra energy. Whatever I am giving here, that will be captured by these atoms or ions. So when these atoms or ions are gaining energy, then what will happen? Suppose I will take a neutral atom, silicon atom, and 4 electrons are present here, and I am giving this voltage. So I am giving energy here. So this electron obviously will come out of the structure, generating one electron and one hole, or by breaking covalent bond, the electron will be free. We are not sending the electron to collide here, but due to this extra energy itself, the electron will gain energy and come out of the structure. Okay. So whatever ions or atoms are present inside this depletion region, due to this heavy amount of electric field strength and applied increased voltage, they will tear out, or the electrons will come out of this structure to generate electron and hole. So this atom will generate one electron, one hole. This atom will generate one electron, hole, one electron, one hole, or even ions are there, means they will be generating electrons or holes. Okay. Now see, the electrons will move in this direction, hole will move in this direction. So what is the net current? Which direction current I'll get? Electrons are moving from P to N, holes are moving from N to P. So what is my net direction of current?
N to P.
Sir, N to P.
N to P. So that is I minority. So if you compare the previous case, here the process is a little bit different, but I am getting the minority carrier. And when the electrons and holes are moving, we'll get minority current. So with narrow depletion region, the electric field strength volt per watt produced by reverse voltage is very high, and this electric field exerts large force on bound electrons to tear out from the atom and increase the reverse current. And this is called as field ionization. Due to the electric field strength, the atoms are releasing electrons, or electrons are coming out of this atom. So that's why it is called as field ionization, which causes the Zener breakdown. So Zener breakdown generally heavily doped diodes and narrow depletion region and occur less than 6 volt. Okay, it is occurring less than 6 volt. If you have done yes, you have already done IV characteristic of PN junction diode and Zener diode. How much reverse bias you have got? Reverse voltage breakdown voltage for Zener. Maybe it is less than 6 or 5.5 or 5.6 volt you have got. You have done or not? IV characteristic?
Yes, so 5 volt.
5 or 5.5, like that you will get. Okay. So that is the reason. So despite two type of breakdown mechanism, Zener diode are commonly used in all breakdown region, because that is the reason why we have not used in the lab PN junction as reverse bias condition, because it will break. But Zener diode are specially designed diodes. Even if high amount of current will flow, it will not break. That's why we have taken PN junction in forward bias characteristic, and reverse bias we have taken Zener diode, and we have observed that one. And another critical thing you will mark, Zener diode and PN junction diode characteristic in reverse bias, one difference is there, like this one. So this will be PN and this will be Zener. So do you mark what is the difference? Tell me, what do you observe? What is your observation by these two graph? Red one is PN junction, Zener is black one. Any difference you mark? Both are increasing current. But anything you mark? Not marking anything. That means both are same. Suppose I will draw.
The PN is wider than.
So this is PN, this is Zener. What is the difference between these two graphs?
Voltage is constant in
Reverse
So,
voltage towards the suddenly increase
in
होगा.
Zener characteristic, the voltage remain constant. Okay, from here to here, voltage remain constant. Even if current increases, voltage remain constant. But Zener, the voltage changes and current also changes. Okay, they are not getting constant voltage. So that is the advantage of Zener. Will use as voltage controller. Okay, now you have understood what is the difference. You may get a question like differentiate between PN junction diode and Zener diode, or avalanche breakdown and Zener breakdown. So how many points you can mark it here? First one is impact ionization, here field ionization, lightly doped, here heavily doped, depletion region wider, here narrow depletion region occurs more than 6 volt, here occurs less than 6 volt in reverse condition, and characteristic, here it is increasing with voltage, here it is constant, voltage constant, current is increases. So how many point I have told you?
So for 5.
5 point. So you can give this 5 point as difference between avalanche and Zener breakdown, or normal PN junction diode and Zener diode. Okay. Once you understand this concept, then due to this constant voltage of Zener, will use as voltage regulator. So voltage regulator means in general all the electronic circuits or any circuit, we require constant voltage. Even if we get the voltage from the source that is not constant, some variation will be there. But if we require constant voltage, then how will get that constant voltage? We may use this Zener diode as voltage regulator. Okay. So let us see how it will be used. So first let me show you this one. So this is a circuit which is generally called as a voltage regulator circuit, and try to understand what is the problem in this circuit. V R RL. Now see, suppose I am increasing the voltage here. If I increase the voltage, then current across RL will increase or not? Initially I have given here 5 volt, then I increase to 10 volt, keeping R and RL constant. Let us take here 100 ohm and here 1K. Now 5 to 10 volt, if I increase, the current across the circuit will increase or decrease?
So increase.
Increase. Now across RL, I'll get voltage. So voltage V1 and V2. V1 when 5 volt is connected, and V2 when 10 volt is connected. Which will be greater? When 5 volt is connected, let us take I1 current is flowing, and when 10 volt is connected, I2 current will flow. So tell me, I1 is greater or I2 is greater?
So I2 is greater.
I2.
I2 greater. So
Yes.
multiply by 1K resistance. So V1 will greater or V2 will greater?
So V2.
V2 will greater. That means I can conclude here the load resistance or the output voltage depend on source voltage. Yes or no? When I increase the voltage, source voltage, my output voltage increases. Similarly, if I decrease from 10 volt to 5 volt or 1 volt, then output voltage also decrease. Yes or no?
Yes, sir.
That means one conclusion, the output voltage of any circuit depend upon the source voltage. Now let us another case where I'll keep I volt constant and change my resistance. Earlier I'll take 1K, now I'll take 2K. Here current will be remain same or different if I keep 5 volt constant. Okay, let us assume I is constant. Okay, current is same. Then what will happen if I change this 1K to 2K into I? So voltage will change or not?
Voltage will be changed.
Voltage will change. That means two conclusion you can say here. The source voltage and load resistance are affecting my output voltage for any circuit, or you can see in this circuit, given circuit, the source voltage, that is V, and load resistance are the two parameter which are affecting V naught. Is it clear to all?
Yes, sir.
Now I'll say I'll connect one Zener diode here. I'll connect Zener diode here parallel to load in reverse bias condition, and I will observe the change in voltage 5 to 10 volt, or the change in source voltage will not affect my V naught, and change in load resistance will not affect my V naught. V naught, by changing 5 to 10 volt, it will remain same. By changing 1K to 2K or 500 ohm, the voltage remains same. If I observe that type of situation, then can I say due to this Zener, I am getting regulated output or constant output?
The constant output.
Means output is not changing, V naught is changing, not changing. Before, without connecting Zener, I am getting different voltage. If I change source voltage, if I change load resistance. Now if I say using this Zener, if I connect the Zener in parallel to load with reverse bias, then even if you change the source voltage or load resistance, output voltage will remain same. If I observe like that, can I say due to this Zener I am getting constant voltage?
Yes, sir.
हाँ कि नहीं? अगर मैं वोल्टेज चेंज करूंगा इनपुट से और लोड रेजिस्टेंस चेंज करूंगा तभी मेरा आउटपुट सेम ही आएगा, तो मैं बोल सकता हूं कि Zener के लिए ही यही हो रहा है.
Yes, sir.
So that is actually, you can say Zener diode is regulating the power, the voltage, or I can say Zener regulator, voltage regulator by Zener diode, anything you can say. So that is what we try to find out here. So for that, this circuit is used. Let us see how this is happening. Now we see this circuit, the same circuit whatever I have drawn is here. This is your source voltage, this is your series resistance, this is your RL, and Zener diode is connected here. So across RL, what I'll get? Vz is equals to output voltage, because the Zener voltage is Vz and that is parallel to RL, so I am getting V naught as Vz. Now if I say current which is flowing across this circuit, what you take? Let us assume current which is flowing here I, and the Zener current is IZ, and load current is IL. Okay. Now, if I apply KCL at this point, what I'll write? Total input current is equals to total output current. Total input current is how much? I equals to IZ plus IL. That is equation 1. I equals to IZ plus IL. Total source current is divided into load current and Zener current. Now, you apply KVL here in this loop. What will get? Minus to plus V. Then here how much resistance I'll get? R. And if you multiply with current, then IR. Then what is the voltage? Plus to minus, that is 0. So VZ equals to V minus IR. You get or not?
Yes, sir. Yes, sir.
That is the second equation. In third equation, the voltage between these 2 points. Across load, what I'll get? Load current into load resistance, that is equals to VZ or V0. That is the third equation. Okay.
Yes,
so
sir.
these 3 equations we observe from this circuit diagram. Very basic equation. Now we'll take 2 conditions because we have observed here this V is controlling my output voltage and RL is controlling output voltage. But at a time, what is the effect of V and what is the effect of RL, we cannot observe. We will take one at a time. That means we'll assume RL is constant while taking V as parameter, and while taking RL as parameter, we'll consider V as constant. Okay. So we'll take 2 conditions here. Case 1, V constant. That means I will not change source voltage. I'll change RL. RL is varying. Case 2, opposite. That means V is varying and RL is constant. Understood? Because these are the 2 parameters affecting my output voltage. Now, using this Zener diode, what I told you, even if I'll change this V and RL, if I get this output voltage constant, then I can say using this Zener diode, I have controlled my output voltage or regulated my output voltage. Yes or no? Are you getting or not?
Yes, sir.
Yes,
Yes, sir.
Yes, sir.
Now see case 1. Input voltage V is constant and load current IL vary by varying RL. इनपुट से वोल्टेज कांस्टेंट मैंने चेंज नहीं किया, RL को चेंज कर रहा हूं, RL चेंज होगा तो तुम्हारा IL will change. Now observing the characteristic, this is your VZ. So VZ is constant, so I can say change in VZ is equals to 0 from the characteristic of Zener diode. Is there
Yes,
any
sir.
change in voltage here? Current is increasing but voltage is constant. So I can say delta VZ, that means change in Zener voltage from the characteristic, it is 0. And I am not changing any source voltage. So I can say del V is also 0. Change in source voltage is 0. Now you put this thing into equation 2. What is equation 2? VZ equals to V minus IR, we have just now calculated. And if I change this VZ, small change in VZ, is due to, I can say, change in V minus change in current. Resistance constant, I am not changing resistance. So change in Vz will be due to change in source voltage minus change in current through the circuit into resistance. Now what is my change in Vz and what is my change in V?
0.
0. If you put 0 here, then what will get? This is 0, this is 0. So I'll get delta I equals to 0 or not?
Yes, sir.
Delta I 0 means the current which is flowing here we have taken as I. So change in this current will be 0. Ultimately it is saying this one. If I am not changing source voltage, source से अगर voltage change नहीं करेंगे तो current भी change नहीं होगा सर्किट में. खाना नहीं देंगे तो तुम क्या करोगे? जितना काम कर रहे हो उतना ही करोगे.
Yes,
No. So source is constant. So current is also constant through the circuit. From observation we can deduce that one, and from mathematical calculation also we have reduced to delta I equals to 0. Now we'll put the same thing here in equation 1. What is my equation 1? I, that means total current I equals to IL plus IZ. So I can say change in I equals to change in IL plus change in IZ. Okay, change in IL plus change in IZ. Now if just now we have observed delta I equals to 0, then delta IL equals to minus of delta IZ. Is it correct? अगर सोर्स करंट चेंज नहीं हो रहा है तो क्या होगा? लोड करंट एंड जेनर करंट will be opposite to each other. That means whatever change in load current, equal and opposite way the zener current will change. Suppose due to increase in load resistance, you can see here, due to increase in load resistance, if IL decreases, the same proportion IZ will increase. That will balance the current. Suppose in this circuit 5 milliampere current is flowing and here 2 and 3 milliampere current is flowing. Now I am increasing this RL so that 2 milliampere current will flow. That means 1 milliampere decrease here. So that 1 milliampere will add it here. So it will be flowing 3 milliampere current in the zener. And zener has the capability, just now we have seen, what is the capability of zener? Even if the current will increase, the voltage will not change, Vz will remain constant. So this zener is connected parallel to this one. So I'll get always constant voltage here. So extra amount of current what is reduced here, that will be added here. And even if the current is addition in the zener, it will not change its voltage. So I'll get same voltage across this load. Are you getting my point?
Yes, sir.
Yes, sir.
Yes, sir.
So adjustment will happen there, and if RL will decrease, then IL will increase. IL will increase means proportionally the IZ current will decrease. Means less current will flow across zener, more current will flow across RL, so that it will compensate and voltage will be remain constant. So this is the first case. Now second case, see, same way. So whatever I have explained, that is written here. When load resistance decrease, supply remains constant, the load current IL increases and zener current IZ decreases equally such that the supply current I remains constant. Okay. Now case 2, suppose I'll vary the input voltage and keeping the RL constant. So if you vary V and keep the RL constant, from the graph we know delta Vz equals to 0, no change in voltage
Zener.
in the Zener, so delta Vz is 0. So if you put that one in equation 3, Vz equals to IL into RL, so change in Vz equals to change in IL into RL. So Vz is 0 means change in load resistance is, load current is 0. That is obvious because load resistance is not changing means load current will not change. So mathematically it is proved. Now if you put this one in equation 1, what do we observe? I equals to IL plus IZ. So change in total current equals to change in load current plus change in Zener current. Now load current is not changing, so this is 0. That means whatever change in source current, that will affect my Zener current. That will affect my Zener current. If V increases, I increases, so that extra current will flow only through the Zener, not through the load. So see here, suppose I will take here initially 5 volt and such that maybe 5 milliampere current is flowing, and here 2 milliampere and here 3 milliampere current is flowing. This RL is fixed, so I am getting some voltage here. Now when I increase 5 to 10 volt, let us assume 7 milliampere current is flowing, so that extra 2 milliampere current will not flow to load, it will flow across Zener. So how much current will flow across Zener now? Tell me how much?
2
is flowing, already flowing.
Yep.
Extra 2 milliampere is flowing. That extra 2 means 2 plus 2, 4 milliampere current will
4
flow
milliampere.
to Zener. Okay, so that the voltage across Zener will not change, and here also the output voltage remain constant.
Constant.
Understood? So this is
Yes,
the
sir.
way how the Zener and load current will adjust themselves such that the output voltage remain constant always. So this is one current increment is actually demerit of Zener diode, any diode, but we have made such that it will be utilized in the voltage regulator circuit. Any doubt? One problem I'll give in the assignment. You should try that one. If you not solve, then I'll solve in the class. Okay. First, let us know how much you think about that. Then we'll go for solving this one. So almost we have completed the diode topic. Only clipper and clamper are there. So next class we'll go for clipper and clamper. And once clipper and clamper is complete, then we'll go for another test. So let me take the attendance, just a minute. Guys, any doubt from the topics what we have discussed today, or we'll wind up? Next class, clipper and clamper will be there. So clipper and clamper is little bit difficult if you don't know KCL, KVL. So try to memorize that KCL, KVL, how we'll put the current equation and voltage in a loop, so that it will be easy. Once I do that 1 or 2 questions, I'll give you to practice and tell me the answer. Otherwise, it is very difficult to understand, because in offline class, when you do this clipper and clamper, students are not generally practice and forgot. So here online means it is a little bit more difficult. So I want from your side full cooperation. So once I solve one or two question, I'll give one or two question to you so that you will practice and tell me in the class how you think what is the output. Then it will be easy. Okay.
Okay, sir.
So Monday we'll start Clipper. Thank you. I have taken the attendance.
Yes, sir.
Now.
Attendance.
I have taken.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you,
Thank you, sir.
Thank you. Thank you.